Uh, Welcome. We're down to a couple, but we're still getting responses back in for the canvanizers, etc. So that's all good. Um, right, just a reminder again, where we will be recording and posting on YouTube as soon as I get the chance to edit it all up, which hopefully will be tomorrow. So our requirements for the next couple of weeks, we'll go through that as well. I think we've just been, or Sebastian's just been talking to Shelley about one of her queries. You guys already got answers to anything that you asked, or you got anything to ask at the moment? Okay. Um,
I might just jump in quickly, Ian. So we haven't updated the marks for the videos yet. I'll try to get them done probably by tomorrow night. And for those of you who send me the calendar directly, thank you. So your marks should be updated for anyone who emailed me. If you check your grades and you still don't have any marks for the Canvanizer and you've already submitted it, please email us directly, and I will sort that out for you. The rest of the assignment should be good. So I've received all the links. If I have any issues opening the videos, I'll reach out to you. Thanks, Ian.
okay. Just to clear up a little bit more on that, the difference between, say, working for a council, which is what we were asked, and developing something for local government or not-for-profits or areas like that. Don't worry at all about the return on investment as far as a dollar value goes. But if you're doing something, it's going to have a return on investment somehow. It's either going to save resources, save time, give better service, and that's the income we're looking for. So it's just non-monetary. So just phrase it in that way, and that's all good. Right. So seminar 4. Well, congrats on completing the videos. Yep, as Savash mentioned, we'll have a look at those as soon as we possibly can and get some marks back to you. Yeah, check the video feedback or the comments we can give in YouTube. If you haven't loaded to YouTube or you've got it set to no comments, then we'll send you the feedback separately. All right, so next couple of weeks, we've got to have the market research and costing report completed, and have a little bit to think about who would be the best supervisor for your, well, sorry, not supervisor is the term we use at our university. What advisor would be best for your project? From the ones we've discussed so far, I think Savash and I are probably the best to cover them. And we can call in anyone else if we need to. But I think we're pretty much right with the two of us here. All right, so reminder, the market research and costing breakdown of marks. The industry analysis is 25%, so that's really important to look at what's already out there. Again, if we use that council type project or the not-for-profit type project, the industry analysis is really what everyone else is doing anyway. Even if nobody's doing anything, well, that's your analysis. You say to the best of your knowledge that nobody is solving this problem, which is really good. Competitor analysis becomes a little bit more difficult if you're looking at the not-for-profit or philanthropic or quality of life type projects. It may not actually be relevant, and in which case you just state that it's not relevant. I think the rest is pretty much self-explanatory. Pricing strategy, we went through that a little bit last fortnight, and the pricing strategy is really about how you get that return on investment. So again, if you're doing it for a not-for-profit or non-commercial reason, your pricing strategy should reflect that. You're giving it away, but how are you going to continue to support, maintain, update, and what income stream have you got to continue the support and development of your product? Critically important. We had one where we developed a talking book reader in the very early days of iPhones, so the vision impaired people could read talking books on their mobile phone. I think it cost us around $30,000 or $40,000 to create this application. and we sold it for $5 per copy because that was the minimum amount Apple would allow us to sell it at. And yes, we got a lot out there, but we couldn't maintain it. So the product actually died off because we did it for philanthropic reasons, not to make money, but we didn't price it correctly so that we could continue maintaining it. And as iPhones changed and things had to be updated, we couldn't afford to actually do those updates, and the product died, which is a shame in a way, but lots of other people came in and there was lots of competition, so it didn't really matter that much. But if we don't allow for that, our products may not exist for very long. And the SWOT analysis, again, if you're looking at going out to uh, venture capitalists or raising capital or justifying your budget in the case of our not-for-profit market, you will need to have that SWOT analysis to show them anyway. So what are we going to talk about this week? Probably one of my favorite ones, actually. And this is the process we have when we're heading towards production. We won't go to full production level, but it's really important that we understand that going from our idea through its prototyping stages to something you can actually have testing on, something you can get out for field trials, is a very involved process. And if you're doing something for commercial reasons, it will actually make up a very, very large part of your cost base. The initial prototyping is usually fairly straightforward. Your proof of concept is very straightforward, but getting something from some what we termed sticky tape prototypes out to something that can be field tested is a really big step. So we'll have a look at how we go about this. And the main things we'll be looking at in three areas. The first one is the software development tools. Now, we've probably all played with the Arduino IDE, and that seems to work, doesn't it? It gets the job done. We can try things out with it. We can change things easily. All great. But there's other options that you really need to know about and that are really, really important when you start to move towards a more commercial product. If you're building some hardware with this, you'll need to make a printed circuit board, PCB. So how do we go about designing those, getting some sample products for testing? How do we get to the point where we've got a commercially reliable printed circuit board to implement our solution? Once we've got a working printed circuit board, we can't supply that to people. It's got to have something to wrap it in, right? So we need to look at how we're going to package in case this, or have a housing for the device. And there's really a lot of different aspects you've got to look at on that. So again, looking at our council one, it's probably going to be out in the weather. So making it rugged, vandal-proof, waterproof, UV stable, all of those things are going to be critically important. If you're doing something for inside the house, normally it's got to be aesthetically pleasing or people won't want to put it in their house. So you've got different things to look at and different ways you can produce something to house your device. And of course, cost is a big part of that as well. And they aren't cheap to make. Well, they are cheap to make, but they've got disadvantages if you use the cheap options. So diving into it, why wouldn't we just use the Arduino IDE to develop our software? It's simple, got lots of built-in libraries, so you don't have to write everything yourself. It's easy to change. You can move it across different platforms. So you could start with a very small Arduino Nano, for example, move it to an Uno, or move it onto the professional, the pro range that they have. And that's great because you can then tailor the platform performance to suit the budget or the requirements that you've got for your device. However, it is incredibly inefficient because it is written to be easy, portable, work with lots and lots of different hardware platforms. They have to write things in a very general manner. So if we look at the speed it takes to run a program that's written using Arduino IDE, it might be 10 or 20 times slower than something written in a more efficient development environment. So if the solution that you're working on is computationally intensive, or you want it or need it to run on a very low power, and low power I mean both in electrical power consumption and processing power, it may not be the best package to use to develop your software. Another big plus with it is open source, which means that you don't have to pay license fees for the executable programs that you develop. And that's really, really important because a lot of the professional packages, professional platforms, actually make most of their money on licensing fees. So they will charge you a set amount of money for every single board that you produce with that software on it. We've got this case with the speaker independent speech recognition platform we use. And I'll let Sebastian say a couple of things about that in a second. But to buy the software wasn't terribly expensive. It was $200. But every time we deploy one of these speech recognition modules, we have to pay a license fee. So that has to be added into your cost. Do you want to make any comments on that particular one, Sebastian?
No, this was an interesting one because typically, if you just search offline voice recognition, you'll see a lot of stuff about Raspi, which is a library for Raspberry Pi. This specific implementation was looking to do the offline voice recognition for specific commands on limited set of commands on an embedded device. So like this one was just on a typical Arduino under one of their development kits with a Bluetooth and a built-in microphone. And the project we were using this for was we were working with Sheila might be familiar with TADVA technology, aged care people. They build custom rehabilitation solutions for people with disabilities. So they took one of the movable beds and they would gonna take their controller guts out, connect it to their own control box, and they had a Google Home solution to make it voice activated for people with disabilities. But Google ended up stopping the support of being able to send strings through Google Home. And in addition to that, even though it was working, they also had some huge delays because they were relying on the cloud. So get the command, send it to Google services, wait for it to get processed and come back. And then, of course, if it's a crucial use of the system, and if the person's internet goes out, especially for people who say live in the rural Australia, it wouldn't be too reliable. So that's why we ended up kind of partnering up with Arduino to build this solution. And now there are a couple of other ones, similar embedded solutions that have popped up. But one of the other ones, I forgot the name of it. I'll look it up as the end goes through the slides. But this other solution, rather than providing the upfront costs, they provide subscriptions, like a yearly subscription, and then a large amount of per device cost, up to $500 per device, even though it does similar things. So different pricing strategies, depending on how you want to market your product.
Yeah. And this raises another really important point to think on. If you're going to use someone else's services like Amazon, Google, and lots of the smaller ones, of course, bear in mind they change their terms of usage, their availability without any real notice to you. So you might have the best solution in the world and all of a sudden Google changes its mind and says, we're not going to support this. You've lost your market as well. So be very careful about outsourcing to other services unless they are easily transferable. Okay, so if we have a look at the Arduino sketch that we've got up here, you can see that we've got things like digital write, delay, digital write, delay. These are part of the libraries that they build in. And the way they actually interact with the hardware is very different to what we're reading here. And there's a lot of code that sits behind those magic orange words. That is the bit that becomes inefficient because that will be written to be transferable to lots of different platforms. So they will write it in a mode that will allow them to do cross-platform development. And you have no control over what's actually happening within these library calls here. And if you're dealing with real embedded systems and real-time systems, then you need to know how long things will take as well. So we run across a lot of problems with using these simplified packages that come with lots of libraries. So what are our options? There are many. This is a little bit more complete development package. And probably the key things here, I'll let Sebastian talk about this one a little bit more because he's more familiar with the MSP than I am. But really the key parts here is that we can create much larger executables because we can have multiple files. This is a diagram of the internal workings of that CPU. And we can get into registers, we can look at the actual data flows, how the ones and zeros move around inside the processor, and optimize our code for this particular hardware architecture. And the third part that's really critical is the ability to embed what is termed assembly language, which is this yellow bit here. This is the actual language the computer speaks. If you think back to the bit where we talked about programming languages, and Hannes gave a fairly good talk on this, our programming languages are becoming more and more abstract. So we have a single command that does a lot of work behind the scenes, right? So that's that high-level languages. Python's a really good example of that. The ability of ChatGPT to create code is a really abstracted version. So I can say, write me a program that adds two numbers together, and I get a Python program that will do hopefully that. That's what we mean by abstracting the language. So we're saying in our language, English, computer do something, and it goes off and then converts all that into, ones and zeros that the computer works in. And assembly language is as close as we actually get to those ones and zeros. So this is just a representation of a string of ones and zeros that is an instruction to the computer. Why would we ever want to do this? We would do this because we have critical points in our code that we want to have the absolute maximum efficiency. And how we get maximum efficiency is dealing directly with the hardware. I wouldn't expect any of you guys will ever have the joy of playing with this stuff. I love it. I reckon it's the best programming language out there, but I'm weird. But as I said, we do this for the sake of efficiency. It destroys any readability of the code because that's gobbledygook, really. It makes it very hard to maintain. You can't port it across to different platforms. So once you write it for one particular processor, the MSP 430 in this case, you can't move it to anything else. It's non-transferable. But it gives us that true efficiency. We can develop real-time systems with hard deadlines. That means we have tasks that are performed in the program that we know exactly how long they're going to take, down to nanoseconds, so that we don't have any of this spinning wheel while we wait for the computer to think of something else and do some housekeeping and go off here and then come back to our program. It's used in mostly control systems, so those sort of things where you need to know when something will be done. So this is the kind of thing that we'd be looking at for a real commercial development. It has a few disadvantages. Usually the first one is cost. These are quite often very, very, very expensive. The signal processing IDE development platform I use for Texas Instruments TMS 320s, the education price for that for one user was around $25,000. So it's very expensive, very powerful, very good, but very, very expensive. And then you had to pay the license fees for every copy of that program that you sent out. So that is a bit of a disadvantage. And the other really big disadvantage is they are incredibly complex to use. So this is not something a hobbyist would be playing with normally, unless they're a really, really keen hobbyist. But they do have that benefit of being efficient, specifically written for the platforms you're using, give you full control of absolutely everything. But they are for expert use only. Any questions on the software development? That was sort of two extremes of it. There's lots of things in between. You can create your own. In fact, if you're a Linux lover, by creating the bootloaders and cross compilers through GCC and making make files, which again is rather complex, but it's completely doable. And GCC will compile for many, many different platforms.
Ian, if you don't mind, I'll share just a couple of points to add to what you mentioned. One of the other benefits of you writing the code at this low level is that the code itself, that the executable that will be stored in your microcontroller will end up being smaller to compare to, say, doing the same thing on using an Arduino type environment. Because with the Arduino type environment, there are some of the packages that makes it easier for you to write that would be included as a part of your executable on the board, where this one wouldn't include that. Another interesting factor about assembly, because it's so close to the machine code and it's so close to the hardware and architecture of your microcontroller and the computer environment that you're looking at, even the syntax of the code can be slightly different because the way the instructions have been written and the way you can call up those instructions can vary very differently between architecture to architecture. And another very kind of a popular example of using assembly and mixing C and assembly is when we're dealing with embedded systems. Imagine you're constantly monitoring a pressure change, and then what you want to do is if a pressure changes, to turn on a warning light or open up a valve, right? So with that setup, an ideal optimized version of that code, you would be putting your program in a low power mode, waiting for an event to happen. And in this particular sense, the event is the change in the pressure beyond the threshold, and then wake up your microcontroller, wake up your system to be able to respond to it. Now, this requires you to be constantly in an infinite loop, and when the interrupt comes in, you need to be able to jump to a different part of your program and be able to handle the interrupt. So in this case, opening up the valve or turning on the light. Now, for us to be able to do that, we need to make sure when we're done with handling that interrupt, we can go back to the previous state of the program. And again, for us to be able to do that, we need to put the current state of the code and registers and your memory into what we call a stack, which holds the address for the next execution, for the next instruction to be executed. Now, all of what I'm talking about, all of this kind of pushing and keeping track of the states and managing the memory, this is done so much more efficiently if we do it as an assembly level, at an instruction level. So that's one of the very popular uses of assembly and C. So you would write your main code in C, but for parts of the code that you want to have that low-level control over assembly and low-level control over the architecture, that's where you kind of bring in the assembly and start writing about it. Yeah. I just want to add those couple of points.
Really good points, actually. And you reminded me about the memory footprint as one of the key factors in writing efficient code. If we use something like the Arduino Sketch, it creates very large code in comparison to writing it, say, in purely assembly language. And you may think that memory is not important because it is so cheap now, and we've got gigabytes in our machines. But memory still takes up a very large amount of silicon in an actual chip. So if we're looking at making things very small, we want to reduce the memory because of the area of the chip that it takes up and the power that it consumes, because large area of silicon will consume more power. So it becomes expensive in other ways. So we'll find that a lot of production microprocessors will only have 32 kilobits of memory. And that, in our modern terms, is tiny. But we write the code efficiently so that it will fit in there, and we have a much lower power, lower demand, and lower cost solution. And that's really important in a lot of cases. Adding a dollar's worth of or a dollar onto the bill of material on electronic devices usually translates into somewhere around $100 in the end price, because of the tooling you need, or the manufacturing, the actual putting things together, how you get the chips on a board, cutting holes in casings and those sort of things. That was an Apple figure, so be slightly inflated anyway. But yeah, if you add anything on, or you have to have a slightly higher power, even though on a individual basis it doesn't look expensive, it actually turns out to add a lot to the end cost of production point. So
Yeah, we have sorry to cut you off. We have a question in the chat about the use of Rust for programming Arduinos. We have Yiffy on the line. I think Yiffy's been looking at Rust lately. Do you have any comments on that, Yiffy?
Well, Rust is more close to C and C++, and the backend is actually still GCC. And the reason why Rust is kind of important is actually if you're working for Microsoft, they have banned to use C++ start any new project because, like we said, even the assembly of C has very good efficiency. Another issue is they are very easy to cause memory leak. And especially also when you use stacks, you could cause memory leaks, and when you use pointer, you could cause memory leaks. So if you're writing a very complicated and large program, they actually not allow you to use C++ anymore. You have to use other programming language, which has the garbage collection built in. Although it gives a little bit of bulkhead to your program you're writing, but it's generally more safe. And if your program becomes too big, the benefits, the efficiency supported actually being outweighed by the risk to cause memory leak.
just to clarify, in case you're not sure what garbage collection is, it's not what we have every Friday at the front. When you allocate some memory to a variable, so you have something and say, right, I want to keep that for later and we'll put it over here. And then you go off and do something else. If you don't have garbage collection, that piece you put away sort of sits there forever and can cause what's termed a memory leak. So then you go back to run through that same routine again and you make another allocation, take up a little bit more memory, go off and do something else. You haven't got rid of those, you add another one in, and your program memory requirements sort of just continue to grow. And that's what's termed a memory leak. The garbage collection goes through and says that's no longer being used. I'll now clear that memory and I'll make it available for reuse. Java does automatic garbage collection, but Java's garbage anyway. I don't like Java. And a lot of the programming languages do. C does not have garbage collection. Assembly language, of course, is so low level. It's got nothing like that, nothing automated at all. So having something that does garbage collection automatically is nice if you have the resources to do it. In most of our embedded systems, we wouldn't use things or languages with garbage collection because it's inefficient use of resources. We program correctly to begin with. Okay, so we now can start looking at the hardware. We've got our software written, we've done our prototype, and this is a couple of examples of the different sort of stages you would probably go through. The one on the left is what we term the sticky tape prototype, and it's basically a whole bunch of individual boards that we bought from suppliers, modules. We sticky tape them all together and put these wires on it, and we've got something fairly quick and easy to do a proof of concept test. So can we gather the data from this type of device? Will it give us the correct readings? Are the components generally okay for what we want to do? And do our first test with it. So this is an inertial measurement unit with I think it's a Bluetooth or just a radio on it. And we use it to measure the movement of children with cerebral palsy. It was very messy, and unfortunately I haven't got one of the end designs here, but it did prove the point. We could get them to work, we could gather the data, but it was incredibly unreliable. Putting something like this out production would be madness because all of these wires tend to break when things are jiggled about. The boards fell apart. It was just horribly unreliable. Sebastian did a fair bit of work with this one, didn't you, Sebastian? They did cause us many, many issues. It's also fairly bulky. You can see by this, it's about what, 50 millimeters by 70 millimeters or so. These were to fit on the hands of very young children. So it was extremely bulky, bigger than their hand, in fact, and caused us other issues in that way. So yes, it did show that we could design something and build something that would serve the purpose, but it was not something we could actually put out in a production or field trial test. What we wanted to do is get it from something like this over to this sort of layout. And this isn't a terribly difficult process, and we'll look in a second how to do it. These are just two examples of stuff we've built internally. This is a hardware text-to-speech board, which takes strings of ASCII characters in and speaks them. It's also the only one that will speak Farsi. Yeah, weird language that these Persian people speak, don't they, Savash?
Yes, yes.
Yes. This was done by one of my PhD students who spoke Farsi and couldn't get a speech synthesizer to actually pronounce Farsi correctly. So we developed this one that would handle multiple different languages. This one is an ultrasonic pathfinder, again, for people with vision impairment. You do see the sticky tape here, but that's only because we hadn't glued the battery housing down. But as you can see, these have very little spare real estate. You cover as much as possible to try and reduce the overall footprint, and not too many loose wires hanging around to vibrate free. None if we can actually avoid it. This one I'll come back to. If you just remember that little crystal sitting there, that tin can, it's one of the issues we had with it, but I'll talk about that a bit later on. So how do we get from our idea using these little prototype boards all stuck together over to something like this? We got, again, lots of options. One that's around, and again, these are just examples. There's so many around, it's not funny. One called fritzing. Fritzing allows us to work from something like this graphical representation of, in this case, an Arduino board hooked up to a breadboard, and we can create our prototype, synthesized prototype within this simulation. From this, which is what we'd look at when we're building it using our prototyping boards, it can produce the schematic. This is the drawing that the engineers use, because this to us is a lot easier to follow than this. So when we're looking at the physical board with its cables coming out and tracing the cables, it's very easy to make a mistake in where things are connected and what they're doing. Whereas in a schematic, it's crystal clear. We can put labels on things saying what they are. We get the values rather than the color codes for resistors and capacitors. So we really want to have this from an engineering perspective. But what we want to do is turn it into a printed circuit board. And things like fritzing will take this and convert it to a printed circuit board layout automatically for us. And it's very simple, very easy, and has the capability of then sending it off to a pre-selected PCB manufacturer and producing a board. As I said, there's lots of these around. All of them have advantages and disadvantages like others. Fritzing I particularly like because it is simple, easy, and you can get your boards quickly and cheaply. There's others. Eagle Autodesk, they have a free limited version for hobbyists. It doesn't really do the simulation, or sorry, it doesn't do the simulation, but other parts of Autodesk stuff will. It allows us to go from the schematic, which is the way we engineers want to see things, and lay it out automatically with a PCB layout. They do these auto routes reasonably well nowadays, but generally you have to go through and fine tune and move tracks around and make it as efficient as possible to fit into the footprint that you actually have. It's scalable, so we can start with very simple single-sided boards and move up to multi-layer boards. It can handle fairly large board areas, and it's cross-platform as well, so you can run it under Linux and Windows, and I think Mac, but I'm not sure on that. Yeah, any comments on Autodesk or Eagle from Yiffy or Sebash?
No, I think as I don't know if you mentioned, but I think with Eagle, some of the versions it limits you to only 2 layers of board.
The free version does. Limited vision for hobbyists includes 2 schematic sheets, 2 signal layers, and
yes.
80 square centimeters.
In a new one that I've been playing around with, and a couple of my students have been using to just as an online free tool, is Easy EDA. I'll post a link to it in the chat. It's similar to fritzing, but Easy EDA links to, I think, both PCBWay and JLC PCB. So you can even generate the bill of materials and see what components are in stock and they're not in stock. FritzLink does the same, but in the past couple of years, I've seen Easy EDA becoming slightly more popular, especially with PCB Bay and JLC PCB. They both kind of neck and neck in terms of Chinese manufacturing. But I think Ian will shortly talk about some of the
Yeah.
fun things about ordering from those guys.
There's many fun things with that. So for hobbyists or small business, they're probably very good ways to go. If we're going to be dealing with it to any further extent, you'd head towards something like Altium. It allows us to do all of these wonderful things, as we can see on these publicity shots that I grabbed, including the physical layout of the board. So it will give you a 3D image of the board and allow you to design your housing from that. So make sure it's got proper clearances. It also gives you hotspot checking, so you can see where the heat generation is on your PCB for cooling. It'll handle a huge number of layers, and I can't remember exactly how much, and it does a much better job of auto routing. But it does come at that cost of price and complexity. From memory, again, it's about $25,000 per license. And to learn how to use it, if you're already a skilled PCB draftsman, the training only takes you 10 days to learn how to use this. If you're learning it from scratch, it's a very long process. But it is complex, but it does a lot of things. It'll give you a full bill of materials, for example. So you'll be able to have a full costing of the board built into it. It allows for multiple revisions. It documents the connections and does many other things. But as I said, it is expensive and very complex to use. So a lot of these packages will link to PCB manufacturers, and they require something called a Gerber file. And you might be wondering what this weird machine up here is. That's a Gerber. That's one of the very early sign writing machines that was available. And they cut out that vinyl lettering you can buy pretty much anywhere nowadays. And just as a point of interest, the reason I like bringing that one up is one of my first companies was actually designing and manufacturing these machines. So we did vinyl cutters and also industrial engravers for doing brass plaques and things. And we used that same standard Gerber format for this two-dimensional cutting of material. And that's basically how PCBs used to be made, is by cutting the copper and then peeling off the bits you don't like. Anyway, that's completely off track. So you can link these to some online stores. The price of this is quite amazing if you're going to some of the ones in China. I've got an example on here, got 3 PCBs, cost us 26 euros, including the freight, I think, on that one. So it's very cheap. However, the quality of the boards you get can be sometimes a little worrying. Even more so if you're going to get them to populate the boards with the components, put them all together for you. And you've got to be aware of this when you make the order. Is it worth receiving the boards and then throwing the whole lot in the bin? It could still be cost efficient compared to buying locally manufactured PCBs. And there are local PCBs in most countries. There are local PCB manufacturers in most countries, and you have a lot more control over the quality there. So my general thoughts are that if you're doing a prototype, small run, just checking to see if something works, yep, use these manufacturers. If you're actually looking at going out and producing something that is critically reliable, then go to a local manufacturer where you will have much more control over the quality of the end product. The big problem you find is they don't actually produce exactly what you asked for. Remember that little tin can I showed you on that board? We specifically asked for one to be at half height. So it's instead of being about 3 or 4 millimeters tall, the full height ones are about 10 millimeters. They put the 10 millimeter ones on because they were cheaper, and that meant we couldn't fit the PCB inside the case. So we had to remove all of those crystals and put the right ones on. which doing it by hand was extremely expensive and time consuming. Next problem with those boards is about 30% of them didn't work anyway, but we expected that. And we just over-ordered and did a quality check on and fixed the ones that we could and threw out the other ones that we couldn't, which is probably not a good thing from a sustainability perspective, but economically it made sense. So if you are going to these online stores, be aware quality may be an issue and be prepared to invest more time to fix faults and bugs that are within them. This is a little bit more upmarket one, and again, you can see this is incredibly cheap because we've got, I forget how many layers, only getting 5 of them, 6-layer PCB, thicker tracks, so we've got less loss in them. So quite a high quality board supposedly, and yet buying however many it was, can't see how many it was, buying however many it was still not a huge amount of money. So buying from these online stores, great for prototyping, but I'm not sure I'd actually use that in a production setting or somewhere where you are going to actually need to guarantee the reliability of the PCBs. So now that we've worked out how to do our PCB, we decide whether we're going to populate them with the components or we can get the PCB manufacturer to do that. Most of the time, it's much cheaper to get the PCB manufacturer to do it because they have the resources, they have better buying power than we would. So you just get them populated and don't try and assemble them yourself. But again, there's that quality issue. So we've got the PCB. Sorry, go on, yeah.
I just want to add an asterisk, a fun little tidbit. Because of COVID and component shortage, sometimes what we've had to do is the manufacturers will run out of a chip. So if we needed to prototype something, we would have to pay for the more expensive development board of a kit, lift that up and put it in our prototype.
Yeah.
Thankfully, it's getting better, but that was just an interesting tidbit to share.
Yeah, it was a fun time in COVID. If you look at why you couldn't buy new cars, it wasn't just that the factories were closed and weren't building cars anymore. It's the suppliers that were closed and all the semiconductors weren't being made because the factories were closed and they could build the cars, but they couldn't put any electronics in them. And cars are now more an electronic device or a computing device than a mechanical device. So looking at what we're going to put the PCB in or our device in, lots of different options here, and it very much depends on where you're going to put it and what the use is. As I said, if you're going to put it into a home environment, you want it to look really pretty. So, is it going to come up? There he is. Very pretty little IoT device. It's my Apple speaker. It does lots of nice little flashing lights at the top if you touch it. And so very aesthetically pleasing. I'll be quiet. And it needs to be marketable in a home environment. People want it to either be invisible or aesthetically pleasing and other things. If we're putting something outside, we need to make sure it's weatherproofed. So lots of different types of housings for different purposes. We'll have a look at a few of them here. The first one we'll have a look at is the Jiffy box, which is this little fella down here. And these are standardized size boxes that you have PCB mountings inside for. They're very, very cheap and they're ugly as sin. So great for things that are going to be indoors, not seen, or in an industrial setting where it doesn't matter, and you've got a very low production run for them. So yeah, they have their uses and we use them a lot. But as I said, they're not something you'd want to have in a home environment or somewhere pretty. And they come in all kinds of shapes and sizes, so you can get something to suit. Probably one of the more common one now is 3D printing, and we've got an example of a little Raspberry Pi casing up here. Absolutely superb for low run prototyping. So if you want to make a manufacturing prototype, which is something that looks like the end device, but may not actually work or may not be exactly fully functional, 3D printing the casing is a really good idea. However, there's a few issues with them. It is very cheap. The plastic is $40 a kilo, and you can make an awful lot of stuff out of a kilo of plastic. But as we can see here, because they work on a layering system, the quality can be a little bit iffy. It has a tendency to warp. It is not particularly good externally. It's not UV stable most of the time, depending which material you use. And it's certainly not waterproof because of this layering. And they're not strong because you're sticking different layers of plastic together, putting a hot layer on a cold layer, and it doesn't actually weld completely so they can come apart. And when you're 3D printing, you've got to be very careful about which direction you print in to get the maximum strength out of them. Print a case like this on a current sort of 3D printer, you'd be looking probably 4 or 5 hours as a best estimate on printing something like that for one. So again, great for one or two off, not so good if you've got a lot to do. Probably the next one up is the rapid prototyping. These type of cases, one here for example, use different methods for printing, but they tend to be very fragile. So they're done to be aesthetically correct, but structurally they are not particularly good. And these are very good for taking out examples or getting customer feedback on what they think of the housing and doing ergonomic checks on them. Lots of other areas that you can use them in, but they're not generally for production. And the last one we'll talk about. Oh, sorry, there's two more. There's vacuum casting, which again is, hopefully that'll get answered soon, is very, very cheap. You can do fairly large runs with it, but it's usually done on very lightweight material. If you think of pots that you get from the nursery, that very thin plastic, that's vacuum cast or vacuum formed. The material needs to be very thin. It needs to be very soft to be able to work in that process. So it's good for stuff that's not going to last very long or for temporary enclosures. The last one is probably the most expensive, but also the cheapest when we get into large production runs, and that's injection molding. With injection molding, you need to create a set of dies that, well, look like this. You inject plastic into them, you pull the die apart, and you've got your finished plastic device that comes out of it. Again, the plastic itself is very, very cheap, so each individual item comes out at very, very low cost. However, making these, and I know firsthand because that company I mentioned earlier, we also made these injection molding dies. And we would charge as a base starting price $40,000 for a small injection molding die before we even started working on it. Now, if you're producing 10 items, that's really expensive. But if you're producing 8 million of them, it turns out really, really cheap because the plastic that you're putting into them and the rate you can produce them means that each individual item is very, very cheap. The next advantage of it is you can get very high quality out of injection molding. You can get very low quality out of injection molding too, but you can get very high quality out of it as well. And that is dependent on how much you spend on creating the dies. Other problems, well, other things with it, to even fire up an injection molding machine, you've got to be looking at runs of 5,000 or more. So you do need that very large quantity, otherwise no one will actually do it for you. There was one other thing I was going to mention on that, which I can't think of. Oh yeah, the range of materials is also quite varied. So you can have very hard plastics, soft plastics, UV stable, and actually make the casing to be very, very suitable for the environment it's going into. But as I said, you need really, really large numbers, large investment to work with injection molding. There are other methods of doing it. We can mill them using CNC machines, which are automated machines to machine things out of a solid block. If you've got an Apple laptop, the cases of those are made from milling because they're made out of a solid piece of aluminium and they just machine out where they don't want the case. But again, that's really expensive. I think that's all we were really going to cover tonight. We're doing pretty well on time. Still got 8 minutes left. Aren't we good? So now we could chat about anything you care to chat about.
We have a question in the chat. Question about grading. I posted a link to my hand sanitizer. And you've had problem with the account. Andrea, I had requested for you to email us your Cambonizer submission. In case I missed it, please email that to me directly. I'll post my email in the chat and I'll submit the marking for it. And then the presentation marks should now be up as well, because I was trying to multitask and just posted the marks now, alongside the feedbacks. I think everyone did a fantastic job. Looking very forward to the future submissions. So here's my email. And if there's any outstanding marks from your Cambonizer, please send that directly to me and I will mark it. The other submissions, if you don't see the mark for them, it means we haven't marked them yet. But because everything will be captured through the system, all of the videos that we have received have now been marked. So if there are any further issues, please feel free to send that to us. And I'll mention this again. Here at Keratin, we are now heading to our exam period. So if in case we miss your email, it might get just lost in a sea of end of semester emails from students. So if you don't get a response from us within the next, let's say within 2 business days, please send that to us again so it pops up in our mailbox.
Okay. I haven't got anything more to add.
Sorry, I have a small question or request for the for the WebEx meetings. I believe the 3rd seminar was uploaded maybe yesterday or today. So if you don't mind, can you just immediately after 2-3 days from the WebEx meeting, can you upload it immediately so we can, if we miss something or we have some audio issue, so we can immediately go through with that one and we can learn the things that you taught in the WebEx meeting, because I have seen the 3rd meeting was uploaded maybe 2 days earlier from now.
Yeah, I think I was a bit late posting the 3rd one. I'll make sure that the future ones are posted in a more timely manner.
Very fine, sir. Thank you.
No worries. Shelly, you had a question? Oh, because you have to raise a hand thing. No worry.
If you're really interested and want to put yourself through it, that channel has all of the past talks on it as well.
Yeah, the YouTube channel.
Yeah, the IoT, I forget what it's called. I set up a separate channel for it.
Also, is there any chance, for example, I want to contact or I want to discuss my idea to, for example, Mr. Andrea, any of my mate, classmate, I can discuss with them. But I have never seen any channel or something to contact with them except this just posting on the.
Yeah, I would recommend just for the sake of privacy, you can utilize the discussion boards.
And if I,
for one part user, they can use all this one.
Sorry, we're getting some feedback from someone. Oh, okay. Yes, Ian, go ahead.
I was just going to say, if students want to pass on their own emails, that's up to them. They're more than welcome to.
Can you guys hear me?
Yeah, we can.
Oh, you can hear me. Wonderful.
Yes.
Sorry, I just have a quick question. So thank you for bringing up my email that I sent previously. So I can't find the market share of my. So I'm Mandurah local government, and we have used companies in Perth previously, but I can't find the market share for them. I don't have, they haven't got their financial reports online. because they're just small WA companies, I would think. So I can't fill in 4 boxes on that rubric sheet with, you know, how it asks for a percentage of market share.
And so Shelley, for that one specifically, that's the explanation you can kind of put under the table, that because these are small companies and their finance reports aren't available publicly, you weren't able to fill the market share. Yeah.
Okay, wonderful, thanks.
Because the idea is to get you to think about the fact that when you're looking at these companies, if that sort of information is available, because project to project can vary, right?
Yes.
Yeah, I understand.
I think with Shelley's, it's a case of just rephrasing everything in the context of local government. So it's not about profit, it's about benefit to community, or it's about savings or other things. So rather than looking at market share, you've got a captive market, all of your ratepayers. So you would look more at what would be the uptake within the community, for example.
Yeah, wonderful. So I'll just put my answers into the squares in the PDF.
How you think they best suit, and if the particular category doesn't suit, think about how a category similar to that applies to local government.
Yes, understood. Okay, thank you.
No worries. I just shared, if anyone's interested, we kept all of these up, so it's all on the IoT6 channel. So if you wanted to see what we did back in 2020, which was, I think, our first session, was it 2020? Yeah, 2020 was the first time we ran it. You can go through and have a look at those. And as you can see, it was a lot of people. We had 4 sessions, so you can watch the same thing 4 times.
Yeah,
It's all a little bit different because it was different people.
I mean, I think one thing that would be especially worthwhile if you watch Valerie's session, because you probably won't get to it in this run of the course. So that was specifically, I think, on big data and cloud, if I'm not mistaken.
That would be probably Seminar 5 2020, maybe.
I found one of them. This is session 7 in the one from 3 years ago. Just waiting for it to play. Yep. And you can see my hairline changing over the years. And Ian's beard getting longer.
I'm getting ready for Christmas. I'm
yes.
Santa Claus.
Yes.
I'm the right build. I've got the right beard. I'm grey-haired. There you go. I can be Santa for everyone.
And in some of the videos, you're probably going to see Ian's dogs on the couch, because that was before WebEx had the backgrounds. See them grumbling in the background.
So these videos are previous entries from other students.
Yep.
No, so these are the previous one of
the
these
talks
sessions.
that we're having now.
Yeah.
But you'll get quite a bit of discussion on the end where students are talking about issues they're having with their projects.
Right. Okay. Yeah.
And we talked about a few different things.
Yeah, especially because there are different projects and we sometimes have different
presentations.
examples. Yeah.
Okay then. Shall I wish you a good morning or good evening or whatever it happens to be, and we shall catch up with you in a couple of weeks. As Savash said, if you've got any questions, email us. Don't get an answer for a couple of days. Please email again and pop it back to the top of our list, because it's a really, really busy time. Okay.
Thank you.
All right, everyone.
And Andrea, if you send me your canonizer, I'll sort out the marking now.
Okay, stop the recording.
Cool.